Okay, hi. Okay, we're going to learn about energy and chemical reactions. Normally, I'm here in the classroom doing this PowerPoint with you guys, and I need to talk you through it. I just can't have you look at the PowerPoint and think what's going on. You really need me to explain. So if you could look at the computer screen over here, I need you to see that, first of all, I'm going to minimize this. I was on my website, and on my website, I'm looking for this thing that says ECH in chemical reactions, right? And it's a PowerPoint. See my finger pointing to it? Yes? Mm-hmm. Okay. So that's what I have up and running. If you happen to have a secondary computer or an iPad or something and you want to have the PowerPoint run separately as you watch my video, you can. And you should definitely have this piece of paper with you as well, because we'll be filling this thing out as we go along, okay? So I'm going to go back to my PowerPoint. So what we're going to be focusing on is keeping track of energy in our chemical reactions. You know, you're mainly seeing the screen, right? Not, okay. Some of these slides I'm going to pop up, we really don't need to spend any time looking at. So what we're really focusing on is when energy is involved within a reaction, you're either putting energy into a reaction or you're taking energy out of a reaction. Hopefully in class, you probably have seen this worksheet, and if you have not worked on this with your teacher, I want you guys to pause the video right now. Well, not right now. I need you to pause it when I'm done giving the instructions. And I want you to think about what exothermic and endothermic are and write definitions for those. And then also answer question number 2. So if you have not already done that, pause the video now and do that. Don't pause. Okay, so now you're back with me, and we're going to just talk about exothermic and endothermic reactions. You have done some exothermic and endothermic reactions in your lab when you did those 9 different experiments of reaction types. And anytime you had to put energy into something, if you had to heat it yourself, or it took energy from the air or the atmosphere in order for the reaction to go, those things are considered endothermic. All right, so even if you heat it, all right, if you heat it, we talk about it being, it takes energy in. So if something is endothermic and you didn't actually heat it yourself, but it took energy in from the room and you were to touch it, what you'd feel is cold, all right, because it's taking energy from your hand into that reaction. Exothermic reactions are the ones that give off energy, all right, and you guys had those by taking a temperature of some reactions, they got really hot. And when you felt it, it was really hot. So that's what we're going to be looking at, is those types of reactions. So I want to talk about endothermic ones here first, okay? So we're not doing anything on your worksheet right now. We will get to filling things on your worksheet. I'll tell you when to fill things on your worksheet, but right now just focus on the words that we have up here. All right, so you know that this side of the arrow are your reactants, and you know this side of the arrow are your products, all right? And what we're looking at is in the term of algebra. If you have to put energy into something to make the reactants do what they need to do to become these products, think about it as an algebraic equation. Energy is some number, some value, something that has to go into a reaction. Y are our reactants, and then what we're going to form are our products, and products are X. So if you look at this algebraic equation, the question is asking which is larger, Y or X, all right? So X is, of course, is the answer. So what we're saying in this particular equation here is if energy goes into something, the reactants are lower in energy than what the products are, all right? So this is a way that chemistry books would typically show how reactions are, and they'd show that those reactants need to have energy added to them, and then they'll form the products, which are going to be higher in energy. So if you looked at your worksheet right now for question number 4, all right, this is the graph that we're looking at right now, and that's what you'd want to do, is show that the energy of the reactants are lower, that you have to put energy into it, and then the energy of the products are greater. So make sure you do label products there and reactants down here. And so that's just our overview picture. Now the chemistry books, when they show it like this, I don't think do a really good job. So we're going to actually look at it in a different story. And oh, look at that. We're looking at some LOL diagrams. All right. Again, don't write anything down yet on your paper. Please don't write anything down because I need to tell you the bits and pieces of the story before you can put the whole story down. So just what we're talking about is our reactants are lower in energy than our products. When you remember LOL diagrams, our starting that we had over here would be talking about what's going on at the beginning of whatever is occurring, and then this would be our story at the end, just like what we had done several units ago. So here under ECH, we're showing chemical energy. And if you remember several units ago, we were ignoring chemical energy because we weren't talking about chemical reactions. Now we are talking about chemical reactions. So we're going to be focusing on this ECH spot right here. So this is showing our reactants are very low in energy. And this one's showing right here our products are very high in energy. And then as you guys recall, when we had arrows going into the circle, we were showing that energy was being put into the system. But as you guys know, from what we were doing in our last units and what I was just describing before, if we're putting energy into this, if we're heating it, heat actually goes under thermal energy. So we can't add thermal energy and put it in the chemical energy spot, right? So we can't say we have low energy for reactants, add in heat, and then have the heat be here when heat, it actually belongs in the thermal energy spot. So what we need to do is we need to talk about what heat is, what that heat energy is when we add that. And what that does is it makes the particles start moving faster. They collide more often. They have a better chance of bumping into the other things that they need to be in, or they have a better chance of breaking the bonds between certain molecules because that extra energy makes them move around more. And so that's what thermal energy is all about. It's that fast moving of particles. So we have to make sure that is part of our story in our LOL diagram. So really, when you take a look at our LOL diagram, we're showing that here we have our reactants that are low in energy, right? And we have them at room temperature, and we're going to heat them. So we're putting energy in, and that energy is now heat energy. So we're still not done with this because as you can see, this is still labeled reactants right there because we haven't made our products yet. All we've done is taken our reactants that are low in energy at room temperature and heated them. So now that they're high in energy, so we still have a reactant. So what will happen next is, since these particles can move around so quickly and they have all this extra energy, that thermal energy will rearrange our particles into new structures, and these are our products that have more energy in them. All right? So really, when you look at the whole diagram, that's the whole diagram. Isn't that impressive? So our story is this. We have room temperature reactants that are low in energy that we're going to heat. We have to put energy into it. They get very hot. There's still reactants that are low in energy, but they're very hot. And the particles moving around so much can bump into, collide, break bonds, and that process means that that thermal energy now becomes chemical energy because now we're making new material. And when that energy of bumping and so forth, making new materials, we end up with room temperature material all over again. And that is our LOL diagram that we're going to fill in for step 3. So I'm going to do it again on my worksheet. So I'm going to explain it one more time. You're going to hear me go through it all. And this time I'm going to fill in the diagram the way that I would fill it in, not left to right, but from the information that I know. Okay? I know I have reactants that are low in energy. I know my products have to end high in energy. That's from this sheet right here. My reactants are low and my products are high. I also know that my reactants start at room temperature. And when we're done having our reaction go, everything's all done, our products should also be at room temperature. Okay? So in endothermic reactions, we're going to add energy into our system. And this energy is actually going to be our thermal energy. It makes the reactants very high in temperature and they're moving around a lot. These are still our reactants. And all this extra energy will allow for the rearrangement of these particles to form those products. And voila! See how I filled that in? Notice I didn't do it from left to right. I did it from the information I knew so I could tell the whole story. And again, this is an endothermic reaction. We're putting energy into this. Okay, back to the PowerPoint. So now we want to talk about exothermic reactions. Okay, in an exothermic reaction, the material is going to give off energy. And so using that same algebraic setup that we had before, if we had this being X is equal to Y plus energy, right? We can see that the stuff on this side are greater than energy because greater in energy because this X is equal to whatever this is plus some number. So this amount of energy here is less than the amount of energy here. So that's where we're going to start. Was saying our reactants are very high in energy and our products are going to end up low in energy. And this time, because it's exothermic, we need to show energy leaving the system. This is why it gets very hot, because it generates energy and it has to leave the beaker or the test tube or whatever the reaction is going on. All right, so that's that same thing that I was just talking about, showing that energy is leaving. So I'm going to move on. All right, so now to put this all into a storyline again, because the reactants are so high in energy, they must generate, just by mixing them or whatever we might be doing with them, they must generate their own energy internally. But remember that energy is given off as thermal energy. So by taking those reactants and putting them in the same container and allowing the particles to bump into one another, they now generate a thermal energy. And so we can see that this is that increase in temperature, how it gets really hot. And that energy then is the thing that has to be released to make it exothermic. All right, so here's that energy being given off. So I'm going to show you the whole big story again. All right, I'm going to go through it on the PowerPoint, and then I'm going to show you how I fill it in on the paper. All right, our reactants are really high in energy, and our products are very low in energy. Our reactants are also at room temperature, but by putting the reactants together in the same container, they generate a lot of energy, and they end up being very hot. This heat came from the mixing of those two reactants. So now the energy in the reactants is much less. Or now it's the products because they're much less. And this extra energy is what's given off as heat. So now we end up with the products at room temperature. So I'm going to do that on my worksheet now. Okay? So in this, we have our reactants are really high in energy, okay? And we know our products have to end low in energy. We also know we start at room temperature before we mix these things together, and after all the energy is given off, they're going to also end at room temperature. So what happens here is all of this energy that's stored in these chemical bonds, once you mix them, is going to start making the reactants very hot. And when they do that, we now have our products. But in order to get rid of all this extra energy right here, this is the heat that's given off, right? That when you touch the test tube, it feels very hot, and now it's back down to room temperature. All right, so that is our story for exothermic reactions. And just like our bar graph that we did for endothermic, what it shows is that our reactants are really high in energy. They lose energy, and our products are very low. So you should be able to label products. Down here are low in energy, and our reactants are very high in energy. Okay? So that's what that next PowerPoint slide looks like, what I just filled in. All right. So some reactions are exothermic, and in order to get that reaction started, you might have to throw a match in or just add a little bit of energy just to get the process started. That energy is something that we don't really look at right now with this, so that's what we're saying. We're not going to focus on activation energy in this area right now because the amount of energy just to get something started is nothing near in comparison to the energy that's been released. You guys have not been able to see me do the Culligan water bottle demonstration yet, but I'm hoping I'll be back and I can do that. But that's just an example of it's an exothermic reaction that throws off a lot of energy, but in order for me to start it, I need to use a match. And that match is nowhere near the necessary reaction that's available to the whole reaction process. Or the video that you guys saw when I was making it with my husband with the bubbles, right? And he had the bubbles all in his hand and I lit it on match. So that little match was such a small amount of energy, but then the big burst of flames and fire that came from his hands from inside those bubbles, that is what we're focusing on with the products forming and the energy that's being released. All right. Right now, we're skipping number 7 because number 7 is not what's on the PowerPoint right here. Okay, so on this worksheet here, number 7, we're going to skip, and we're going to actually go to this last problem right here with number 8, and that's what you're going to see on the PowerPoint. All right, so it says, as solid ammonium nitrate dissolves in water, the resulting solution forms. So this is our end result of what we're going to be talking about. So by just looking at it, do you think this is endothermic or exothermic? All right, my husband is totally right with that. If you notice that the energy is going in, that's endothermic. But, okay, I'm going to go back to our worksheet here. Some of you guys might have noticed that the example endothermic I gave you had going in on the first circle. And then the example for exothermic had the energy going out on the second circle, right? So you're probably looking for certain patterns of how to distinguish endothermic from exothermic. And the pattern is arrows going in are endothermic and arrows going out are exothermic. Arrows going in can happen either in the first circle or the second circle. All right, so there's no distinct pattern that it can have for these. All right, so the story on this one is that we have room temperature materials. All right, and our reactants, in this case, which is ammonium nitrate, are very low in energy, okay? This takes in energy from the reactants themselves and gets incredibly cold, all right? So what we're showing is that just by taking the reactants and putting them together, it gets incredibly cold, and now we've made our products which are higher in energy. Because it is so much colder than the atmosphere around it or your hands or the tabletop, energy is brought in to bring it back up to temperature. That's the story with this one. All right, so endothermic can be heating right here. This would be heating if you put it in this one, if we put a Bunsen burner on it. But this one is spontaneous, that if you were to just put ammonium nitrate and then water together, each ammonium nitrate and water, the amount of energy that they have separately is very, very low. But when you put them together and they started at room temperature, they'll drop in temperature incredibly and immediately form this product. And so they take in energy from the atmosphere to make our products at room temperature. So that's what you're going to be filling in on question number 8. And since this one's considered endothermic, how would our graph look? Okay, remember you're adding energy in, so our reactants are low in energy and our products are high in energy. So these would be your products and these would be your reactants. All right, so make sure you just go back to this, and if you need to, you can pause the video and put that information in. And then when you're done with that, we're going to go back and do the last question on this sheet, which, by the way, are not in the PowerPoint notes because I believe this is the last slide. I'm going to hit enter. Yep, that's the last slide. So we're going to just focus on this particular question right here. So what we have is hydrochloric acid is added to sodium carbonate. Hydrochloric acid, because it says 3 molar, it's an aqueous solution because it's not concentrated, is added to sodium carbonate. Sodium being a +1 charged ion, carbonate being a -2. We have to write the formula like this. It says it's a solid. The contents in the test tube immediately start bubbling and getting warm. We have carbon dioxide gas forming, so CO2 gas. Water vapor, as a vapor means you have a gas as well. And then also sodium chloride is going to form. And sodium chloride, since it's in water, will dissolve, so we'll have aqueous sodium chloride. All right. It's also saying that it's getting warm. So now we have to think, are we adding energy at the end? Or at the beginning here, or will we be adding energy at the end if it's getting warm? Okay, hopefully you guys are writing energy on this side because energy is being released. It's not being added in. Okay, so when we look at the amount of energy that our reactants had versus the amount of energy that our products have, because they also are releasing energy, which one's greater in energy, our reactants or our products? Okay, you should be saying the reactants are greater in energy. So we're going to put a lot of energy in our reactants, and our products are going to have not a lot of energy. Okay? Everything starts at room temperature, and it's going to also end at room temperature. So what's going to happen now is, because there's all the stored chemical energy as the particles mix, right? As they mix, this stored energy will become thermal energy. It will become very hot. Our products are now low in energy, and all of this extra energy that's heat energy will be escaping as temperature that you feel when you touch the test tube. And now we have finished this, and you can see that this is an exothermic reaction. And exothermic reactions start with high energy reactants and end with low energy products. Our reactants are high in energy, and our products are low in energy. All right. So what your job is to do now is, if you didn't catch everything in this, if things didn't make sense, you need to watch my video again. Go through the examples, go through the PowerPoint, look at the work that I did on the worksheet here with you, look at the PowerPoint, and make sure you can make sense of it. Because the next time you come to class, you'll be getting a practice sheet like this where I need you guys to fill out your LOLOL, because that's what they are. LOLOL diagrams on your own, given the storylines, and you'll need to figure out if something's exothermic or endothermic. All right, that's the end of my video. Bye.